Welcome to ALP Chemistry on Video. This is a live recording, and in class I have Jennifer with me, so if you hear me answer questions, that may be a question for Jennifer. And this is the second half of the lesson on Chapter 11, which is Atomic Theory. And just to remind you where we are, we're talking about valence electrons. And valence electrons are the outermost electrons of an atom. And it is the valence electrons which determine the chemistry of atoms. And the reason for that is that it's kind of like bumper cars. When bumper cars run into each other, it's the outer bumpers which make contact. So it's not the things inside the bumper car which are going to contact each other. It's actually the bumpers on the outside. And the valence electrons are kind of like the bumpers in that sense that the inner electrons are shielded. So the inner electrons inside the valence electrons can't run into each other. It's the valence electrons that run into each other. So it's the valence electrons that determine the properties of an element. And we've done all this work to figure out how to calculate or how to work out an electron configuration. And so that's great. You can work out an electron configuration. But how does that help us understand chemistry? Well, if you know the electron configuration, what that will do is help you to understand the periodic properties of the elements. Why elements in the same family have similar properties. And the reason for that is that their electron configurations are similar. So elements with similar electron configurations will have similar properties. And in fact, that's how the periodic table was first made, because the person who made it realized that certain elements have similar properties, and he put elements with similar properties in columns. And so those are how the families came to be. Now, for example, if you think about sodium, sodium has the electron configuration square bracket Ne 3s1. And potassium, which is right below it in the periodic table, has the electron configuration square bracket Ar 4s1. And so they're both S1. And in fact, all the elements of the alkali metals, all the elements that are in the first column of the periodic table, are all S1. And because they're S1, they have similar properties. And I've got some videos that will show you an example of that. So let's switch over to YouTube. And hopefully this is going to come through on video. So let's go to here. Now what you're going to see in this video is what happens when you drop the alkali metals in water. And it turns out they all react with water. So let's see what happens. So what we're going to do is we're going to start with lithium at the top of the alkali metals, and then they're going to go down and keep working down the periodic table and keep adding other elements to water. So they're going to start with lithium, then they'll do sodium, then they'll do potassium, and so on. So let's play this. So here is lithium, and that little speck on the top right is a piece of lithium, and it's reacting with water, and they've just taken a match and lit the little piece of lithium on fire. And what's happening is it's producing hydrogen, reacting with water to make hydrogen, and the hydrogen can burn, so they just lit the hydrogen on fire. So now they're going to do sodium. They're going to drop sodium in water. And again, up at the top right is a piece of sodium in water. And again, they're going to light that on fire. And you might recognize that orange color is the atomic emission of sodium. Now they're going to do potassium. And potassium reacts right away with water. And potassium again. And now they're going to do rubidium. And then cesium. And notice that they all react with water, although they react with water a little differently. So they're similar, but not exactly the same. And I have another video. Now this one is from a British TV show called Brainiac. And Brainiac, when they did this, they kind of enhanced the effect with some explosives, but it's still kind of a fun video. So I'll show it to you.
Whether you've left school or you're still at school, you can appreciate the sheer fun, mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. Look. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkaline metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay, good luck.
Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes! That is more like only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkaline metal we can legally use.
Yes, Richard, cesium, the emperor of alkaline metals, particularly nasty to go off at any time.
And that's it.
Oh, yes.
I like it already. Now what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the line.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, franklin. But for some reason they wouldn't let us have any of that. So there you go. Today's lesson.
Never mixed alkaline metals with water.
Like I say, they enhance the effects with some explosives, but it's still kind of fun. And Mythbusters actually tested this because they claimed it would be like a hand grenade in a bathtub. So the Mythbusters put a hand grenade in the bathtub to see what it would look like, and then they put some of the sodium and potassium. They didn't test rubidium or cesium because it's too expensive to get, but they tested some of that, and they tested like something like 25 kilograms of sodium and potassium in the bathtub. Now, you saw they were using little tiny amounts, but I think they got a similar effect. I think they cracked the bathtub. I don't think they completely destroyed it. But in Mythbusters, they were able to crack the bathtub, but it took them like something like 10 or 25 kilograms to do it. So it was a whole lot. But anyway, so you see what happens, and all the alkaline metals do it. When you drop them in water, they all react with water, but they don't react exactly the same. And when we get a little further, I'll show you why they don't react exactly the same. It also explains why the noble gases aren't very reactive, and they're not very reactive because their orbitals are full. And having full orbitals seems to be very stable for the atoms. Once they've got full orbitals, they don't like to change. So they don't want to lose any electrons and then have some partly unfilled orbitals, and they don't want to gain any more electrons. They're happy just the way they are. So that's why the noble gases don't like to react. So let's look at some properties in relation to their electron configurations and the orbitals. And the first property we're going to look at is atomic size. Now, if you think about orbitals, remember that different size orbitals have different energies, and the larger orbitals have higher energies. So, so it turns out that the atoms that have the largest orbitals will have the biggest size. So, if you remember that as we go down, the row numbers increase and the orbital number increases. So you're going from 1s to 2s to 3s, 4s, and so on. So as you go down, the orbital number increases. Actually, it's called it's the principal atomic number, is what it should be called. Principal atomic number increasing, and the size is increasing as you go down. So going down the periodic table, it's kind of easy to see that the size of the orbital goes up, the size of the atom goes up. Going across the periodic table this way, the trend isn't quite so easy to follow. But basically what happens is, as you go across the periodic table, the orbital number, the principal number, isn't changing, right? Because as you go across, if you go across a row, like if you're in the third row, it's the third principal atomic number all the way across. So the orbital size stays the same, but the nuclear charge is increasing. And what that does is tend to shrink the orbitals a little bit. So the principal number is not changing. But the nuclear charge is increasing. And the size goes down. Because the nuclear charge tends to pull the electrons closer. So the trend for size is that as you go this way in the periodic table, size goes up. So if that's the case, what do you think the biggest element in the periodic table is? What element would have the biggest atom? So if you look at your periodic table, look and see if you can see which element do you think would have the biggest orbital. FR, right, FR, because it's in the bottom left, so the biggest atom is FR. What do you think the smallest atom would be? HE, yep, HE is the smallest. So HE is the smallest, and FR is the biggest in terms of size. Okay, now that takes care of the size property. Let's talk about how the size affects the atomic properties. Further the electrons are from the nucleus of an atom, the easier they are to remove, because the electrons, which are negatively charged, stay in the atom because they're attracted to the positively charged nucleus. So if the electrons are further from the nucleus, the nucleus isn't going to be able to hold on to them as strongly, so they'll be easier to remove. So the larger the atom, the easier to remove an electron. And this property is called the ionization energy. The ionization energy is the energy required to remove an electron from an atom. And atoms that are easy to steal electrons from, the ionization energy is low. So basically it takes work. It takes work to pull an electron out of an atom, and work is considered to be equivalent to energy in chemistry and physics. So if you think about electrons being held into an atom because they're negatively charged, the nucleus is positively charged, you have a force of attraction between opposite charges. To get that electron out of an atom, you have to put some work in and pull it out. So the stronger the electron is held, the harder you've got to pull, the more work it is to pull it out of the atom. But if you have a big atom where the electrons aren't being held very strongly, then it's fairly easy to pull the electron out. So if it's easy to steal the electron from an atom, the ionization energy is going to be low, and the atoms that hold on to their electrons most strongly will have the high ionization energy. Right, because you have to put a lot of work in to pull the electrons out. And it turns out that big atoms will have low ionization energies. So the trend for ionization energy is the opposite for the trend for size. So ionization energy increases as you go up. And the ionization energy also increases as you go this way. So overall, the trend for ionization energy is basically this way. So this is increasing ionization energy. So it's the opposite trend to the size. So what atom do you think would have the biggest ionization energy?
Biggest would be HE.
Right. So He would have the biggest ionization energy. And the smallest?
The FR.
Right. Fr should have the smallest. And notice that was the trend we saw with the reaction in water. That reaction with the alkali metals in water, where you have the alkali metals, which are the first column in the periodic table, that as you go down the periodic table, the size gets bigger, and the easier it is to pull the electron out, and the faster the reaction. You remember lithium, had a very slow reaction. You had to ignite it with a match. But cesium had a very fast reaction, which blew the whole side of the dish out. So that kind of helps us understand why that happens. So they all have similar properties, but not exactly the same, and the reason is for their atomic size and their ionization energy. Note that metals are on the left side of the periodic table, so left and below. And metals tend to have low ionization energies, and nonmetals tend to have high ionization energies. So what that means for the metals is the metals tend to give up their electrons easily. And that's why metals tend to form positively charged ions, because they don't hold on to electrons strongly, they give them up very easily. Whereas nonmetals, which are in the top right of the periodic table, don't like to give up their electrons, and they'd rather gain electrons when they form ions. So that helps us to understand ion formation a little bit. Opposite to ionization energy is electron affinity. So ionization energy is the energy you need to pull electrons out of an atom. Electron affinity is the opposite, the energy given off when you put an electron in. And we could do the trend for electron affinity, but we're not. Instead, we'll do the trend for electron negativity, which is in fact very similar to electron affinity. Electron negativity is the ability of an atom to attract electrons, and it's actually on a relative scale. So they don't give the exact number for energy. It's a relative scale just from 0 to 4. If you think about size, smaller atoms tend to attract electrons more strongly. So the atoms with the highest electronegativity will be on the top right because they're the small atoms. Atoms with the lowest electronegativity will be on the bottom left. So they also follow the opposite trend to size. Bigger atoms are going to have low electronegativities, and small atoms will have high electronegativities. Which atom do you think would have the lowest electronegativity in the periodic table? FR, yep, you'd expect FR would have the lowest electronegativity. And what element do you think would have the highest electronegativity? Yeah, you'd expect He to have the highest electronegativity. In fact, however, if you've got one of those black periodic tables, which I notice you don't, Jennifer, but if you get one of the black periodic tables, and I'll just wait just a moment till you grab it. You'll notice that the electronegativity is actually on those black periodic tables, and it is the number which is just below the atomic. No, it's not just below the atomic number. It is just above the electron configuration, I think. There it is. Yep. So if you see where the electron configuration is, it's the number just above the electron configuration.
Okay.
So look in the periodic table and see if you can find the element that has the lowest electronegativity. So look at the electronegativities. See if you can find the element that has the lowest electronegativity.
0.7, which is FR.
Which is FR. So FR is 0.7. So you were correct. FR has the lowest electronegativity, 0.7. And see if you can find the element with the highest electronegativity. No, look at the actual numbers of electronegativities and see if you can find the element that has the highest electronegativity. You predicted it would be helium, but see if you can find the element that has the highest electronegativity. Nope, not neon.
Can't see.
In fact, helium and neon don't have any electronegativities listed. So what element has the highest electronegativity? Of the elements that have an electronegativity listed, what element has the highest electronegativity?
Hydrogen?
Nope. The electronegativity of hydrogen, I think, is only 2.2, 2.20.
Was it 157? No.
Keep looking. Keep going to the right, because it's going to keep going up as you go to the right.
It's only right in front of me.
It is right in front of you. Keep looking. Should be on the right, and should be near top right.
There's so many numbers right in front of me, it's hard to see. Oxygen?
Not oxygen. Look one to the right of oxygen. So what's the electronegativity for oxygen?
1.429.
Let me take a
Is
look.
it?
I don't think it's 1.429. It should be. Oxygen is 3.44. Oxygen is 3.44.
Okay. Oh, fluorine?
And fluorine, what's the electronegativity of fluorine?
3.9.
Right, 3.98. And in fact, fluorine is the element with the highest electronegativity. That's okay. Why do you think fluorine's got the highest electronegativity, not helium? What do you know about helium? What family is helium in? It's in the noble gases. What do you know about noble gases?
The electrons are full.
Their orbitals are full. And because their orbitals are full, what kind of properties do they have?
They have low oxidation state.
Well, in fact, they have zero oxidation state because they don't like to react. They don't like to form ions.
Okay.
So, because electronegativity is the ability of an atom to attract electrons, helium doesn't want to attract any more electrons because it's already happy the way it is. It's got full orbitals. So the element that has the highest electronegativity is actually fluorine, not helium, because helium doesn't want to react. Okay, so now that we know all that, let's try to work out some trends here. So, of the two elements, beryllium and barium, which do you think has the largest size? So find beryllium and barium in the periodic table. And once you've found them, see if you can think which has the largest size.
Well, one of those 1.57 and the other one's 0.89.
I think you're looking at the electron configuration, the electronegativity. We want to think about the size. You have to look at the size trend. If we go back to where we were talking about size, and remember what the size trend is. The size trend is, as you go down, you get bigger, and as you go right, you get smaller. So basically, as you go down and left, you get bigger.
So BA is smaller than BE.
Actually, no. BA is bigger than BE. So the larger of the two would be BA, because BA is further down the bottom of the periodic table.
Okay, so whenever these ones, it always goes bigger the smallest.
It goes, when you go down, you're getting bigger.
Okay.
When you go down, you're getting bigger. And when you go left, you get bigger.
Okay.
So going left and going down, you get bigger. So, of potassium and barium, which do you think is bigger?
Barium.
And why do you think barium is bigger?
That's below potassium and over to the other side.
Right. So as you go to the right, you would get slightly smaller, but as you go down, you get quite a bit bigger. So barium would be the bigger one. In fact, I think I meant to do this one. I probably meant to do potassium and calcium. So if you do potassium and calcium, which one do you think is bigger? Actually, it gets smaller as you go to the right.
Oh, okay. So
It's bigger as you go to the left. So it's potassium. Potassium is the bigger one. Fluorine and iodine?
Okay, so it's going to be bigger towards the bottom.
Bigger towards the bottom.
So I.
So I is the bigger one. You got it. Okay, now let's think about ionization energy. Of beryllium and barium, which do you think has the highest ionization energy? And remember, big atoms have low ionization energy, small atoms have high ionization energy.
Okay, so low have high and so BE then.
Right. It's the opposite trend to size. So once you find out which one is larger, the smaller will have the higher
And
ionization
next
energy.
one's going to be calcium.
Right.
And next one's going to be fluoride.
Right. So the smaller one will have the higher ionization energy. Okay, and And now we've got, I think this is our last one. So what we want to do here is arrange the elements from smallest to largest, and then list them from smallest to largest ionization energy. So sulfur, sodium, and oxygen. We want to list those from smallest to largest. What do you think the smallest of those three would be?
Okay, I just gotta find NA. NA would be the smallest. And then oxygen would be the next. No. Would oxygen be lower than sulfur?
What's the trend? As you go down, you get bigger or smaller?
As you go down, you get smaller, bigger. As you go down, you get bigger.
As you go down, you get bigger. So in terms of oxygen and sulfur, which one's bigger?
Or sulfur.
So sulfur is bigger than oxygen. Okay? Now compare sulfur and sodium. Which one's bigger?
Sulfur.
Actually, no, because as you go right, you get smaller. As you go left, you get bigger.
No.
Sulfur and sodium are in the same row, and sulfur is to the right of sodium, so sulfur is actually smaller than sodium. Okay, what about ionization energy? What do you think the trend for ionization energy would be in those? So this is the size trend.
Trend is, as you go to the right, it increases. And as it goes up, it increases. So like these ones would be the smallest, and then as they go here, they get bigger, and as they go up, they get bigger.
Right? So in terms of these,
So
compare them two at a time and see if you can work out.
SP is going to be
So S and O. Of S and O, which one's bigger? Has the higher ionization energy?
O.
Yep. So in terms of O, S has a smaller ionization energy than O.
And then, what's the other one?
S and Na. Compare S and Na. Which one has the bigger ionization energy?
S. No, NA would be small.
Na would be smaller than S, right. And notice it's the opposite trend to size. So once you get the size, it's just the opposite for ionization energy.
Nice, okay.
Okay, let's do the size for these. So SB, N, and S, and AS. So try and get these in order of size.
So SP and so nitrogen is bigger than autonomy. SP.
As you go down the periodic table, what's happening to the orbitals? Are the orbitals getting bigger or smaller as you go down the periodic table?
Bigger.
They're getting bigger as you go down the periodic table.
So SP is bigger than N.
SB is bigger than N. And what about AS?
AS is bigger than SP.
AS is smaller than SB. And AS is going to be bigger than N. So the smallest is at the top, and as you go down, they get bigger. What about ionization energy? Just the opposite. Yep. SB less than AS less than N. And I think we've come to our last slide for the lesson. That's it. So now you can work on the assignment, and that's it. Should be ready for the test after that.
You might have to record that. You have to like tell me the same thing and then move on. It's embarrassing.
So we're all done. So I'm going to stop recording. Good luck. For those of you on video, good luck with the rest of the chapter, and let me know if you have any questions.